At 60 meters deep, inside a dark underwater cave, mistakes do not stay small. They multiply. A wrong turn becomes more gas burned. More gas burned becomes more stress. More stress becomes faster breathing. Faster breathing becomes less time. And once visibility disappears, the numbers begin closing in from every direction. Over the last several videos, many of you in the Commander Puzzles community have been doing something remarkable. You have been running the gas math, calculating oxygen exposure, questioning Nitrox at extreme depth, debating Narcosis, estimating how quickly 5 divers could destroy visibility inside a silty chamber, and asking whether a single cylinder could ever provide enough reserve for a deep cave emergency. So today, we are going to put those questions together. This is not an official forensic report. The complete GoPro footage, synchronized dive computer records, exact gas mixtures, and final investigative findings have not been publicly released. But the laws of pressure, gas consumption, and diving physiology were already operating inside that cave. Those laws do not care about experience. They do not care about confidence, and they do not give second chances simply because a diver believes there is still time. This is the fatal math of the Maldives dive. Let's begin with the number that appears again and again in this case, approximately 60 meters. At the surface, the human body is under about 1 atmosphere of pressure. At 10 meters, that becomes roughly 2 atmospheres. At 20 meters, 3. At 30 meters, 4. At 40 meters, 5. At 50 meters, 6. And at 60 meters, approximately 7 atmospheres of absolute pressure. That matters because a diver's regulator must deliver breathing gas at the pressure of the surrounding water. A breath taken at 60 meters therefore represents about 7 times as much gas from the cylinder as the same breath taken at the surface. The diver is not necessarily breathing 7 times faster, but each breath costs far more. Now let's put a simple number on it. Imagine a calm diver with a surface breathing rate of 20 liters per minute. At 7 atmospheres, that becomes approximately 140 liters per minute from the cylinder. That is, while calm. Now add swimming, add depth, add darkness, add current, add poor visibility, add the mental workload of managing other divers. Add the sudden realization that the exit is not where you expected it to be. A stressed diver may double the surface breathing rate. 40 liters per minute at the surface becomes approximately 280 liters per minute at 60 meters. That is the first major point. At extreme depth, panic does not merely feel dangerous. It becomes mathematically expensive. The cylinder begins disappearing at a rate the diver may not fully appreciate. A pressure gauge can still show gas, but that does not mean there is enough gas to escape. Those are 2 very different questions. The wrong question is, do I still have gas? The correct question is, do I have enough gas to leave the cave, help another diver, ascend safely, and survive the worst reasonable emergency beginning right now? At 60 meters, that distinction can decide everything. This is where several viewers raise the single cylinder problem. Even a full cylinder is not a large reserve at that depth. Suppose a 12-liter cylinder is filled to 200 bar. That represents roughly 2,400 liters of gas at the surface, before accounting for reserve pressure and real-world limitations. At a calm depth consumption of 140 liters per minute, that theoretical supply is only around 17 minutes. But that is not a safe bottom time calculation. It ignores the gas required for ascent. It ignores reserve. It ignores decompression. It ignores gas sharing. And it assumes the diver remains calm. At 280 liters per minute under heavy stress, the same theoretical gas supply could be consumed in under 9 minutes. Again, not 9 minutes of safe diving. 9 minutes before the cylinder is effectively exhausted under that simplified example. And in a real emergency, one diver may need to donate gas to another. Now 2 people are breathing from 1 cylinder. The supply can collapse even faster. This is why a 5-minute look inside a cave is not truly a 5-minute commitment. The diver still needs enough gas to reverse direction. Travel back, leave the overhead environment, ascend from extreme depth, and handle any decompression obligation created by the dive. A few minutes inside can require a much larger reserve than the casual phrase, "just a quick peek," suggests. Now let's move from the cylinder to the brain. Many viewers asked how several experienced divers could apparently make the same mistake. The answer may partly involve nitrogen narcosis. At greater depth, the partial pressure of nitrogen rises. Nitrogen can exert a narcotic effect on the nervous system. Divers often compare it to alcohol intoxication, sometimes calling it the martini effect. But that comparison can be misunderstood. Narcosis does not always make a diver visibly foolish. A diver may continue swimming, read instruments, respond to hand signals, and believe everything is under control. The deeper danger is that reaction time can slow, attention can narrow, memory can weaken, problem solving can deteriorate, risk can feel less serious, and confidence can remain high while actual performance is declining. In other words, the diver can become worse at thinking and worse at recognizing that the thinking has become impaired. That is especially dangerous in a cave. A cave emergency may require several decisions at once. Where is the exit? How much gas remains? Where are the other divers? Which opening did we enter through? Are we ascending or merely moving into a higher section of the chamber? Should we stop, turn, search, or share gas? A diver who is even mildly impaired may take longer to answer. At 60 meters, longer answers consume more gas, and more gas consumed creates more stress. This is how the problems begin feeding each other. Now we need to address an important technical point from the comments. If a diver were breathing ordinary air at 60 meters, the oxygen partial pressure would be approximately 1.47. That is high and near the range where oxygen exposure becomes an important concern, depending on duration and workload. But it would not automatically mean that every diver would immediately convulse. However, if someone were breathing Nitrox 32 at 60 meters, the oxygen partial pressure would be approximately 2.24. That is far beyond commonly accepted operating limits. It would create a serious risk of central nervous system oxygen-toxicity. The exact gas in each cylinder therefore matters enormously. Was everyone breathing air? Was nitrox used only in a spare cylinder intended for a shallower depth? Was a cylinder mislabeled, misunderstood, or used outside its intended range? We do not yet have enough verified public information to answer those questions definitively, but viewers were right to raise them. The gas mixture changes the physiological risk. Now let's move to the cave itself. Another common question is, why couldn't they simply turn around? Why not follow the bubbles? Why not shine a light toward the entrance? Because inside a silty cave, the environment can stop providing usable visual information. The exact time required to destroy visibility depends on the chamber size, sediment type, fin movement, water flow, and diver behavior. So there is no honest way to say that visibility definitely reached zero in a precise number of seconds. But the physical process is well understood. 5 divers swimming, turning, searching, or rapidly changing direction can disturb an enormous amount of fine sediment. The particles rise into the water. Light reflects from them. The beam from a torch no longer illuminates the wall ahead. It illuminates the suspended silt directly in front of the diver's face. Instead of seeing farther, a brighter light can create a brighter cloud. The cave becomes visually unreadable, and bubbles do not necessarily point toward freedom. Bubbles rise toward the highest available surface. Inside a cave, that surface is usually the ceiling. They can travel along cracks, collect in pockets, or move away from the entrance. Following bubbles in an overhead environment is not the same as following bubbles in open water. Without that physical reference, the diver is left with memory, orientation, depth, and guesswork. And depth can be deceptive. A diver can become shallower while moving farther into a cave. A passage may slope upward, but still lead away from the exit. The computer may show that the diver is ascending. That does not mean the diver is approaching open water. This is one of the most dangerous misunderstandings in three-dimensional cave navigation. Up is not always out. Now imagine the group reaching a junction after visibility has collapsed. The obvious route may feel correct, but if it leads deeper into the system, every minute spent inside it increases the distance back. That adds more gas use, more uncertainty, and more stress. The math tightens again. Some viewers asked whether 5 divers could have stayed together through this. A group can enter as one team and still become functionally separated. The group does not need to spread across hundreds of meters to lose coordination. Now add gas sharing. The original emergency now creates a second emergency. This is why deep cave diving procedures focus so heavily on reserve, redundancy, team control, and exit discipline. Not because divers expect everything to go wrong, because they must be able to survive when one thing does. The Maldives tragedy appears to involve several potential problems occurring in the same narrow window. Extreme depth, rapid gas consumption, possible narcosis, possible uncertainty over gas mixtures, an overhead environment, silt, confusing cave geometry, and limited reserve. Any one of those factors might be manageable alone. Combined, they can become overwhelming. That is the real meaning of fatal math. It does not necessarily mean the outcome was predetermined before anyone entered the water. It means that once enough margins were removed, the environment may have stopped allowing a workable recovery. The divers may still have been alive, still moving, still thinking, still trying. But the number of available solutions may have been shrinking faster than they realized. Now we reach the questions that physics cannot answer. The sixth diver, and the recovered digital evidence. Why did the sixth person reportedly remain on the boat? Was it illness? Concern about the plan? Equipment? The depth? A personal feeling that something was wrong? We should not invent an answer. The surviving diver's full account has not been publicly released, and refusing a dive does not automatically mean the person predicted the tragedy, but that testimony could reveal what the group believed they were about to do. Was the plan presented as a brief inspection near the entrance? Was deep penetration discussed? Were gas limits reviewed? Was the cave layout understood? Were concerns raised before the others entered? The sixth diver may be able to explain the intention. The cameras and dive computers may explain the execution. The computers could show depth, time, ascent rate, alarms, and how closely the profiles matched. The cameras could show visibility, team position, the first navigation problem, and whether the group recognized the danger early. When synchronized, those records may reveal the moment the dive changed. Not necessarily one dramatic instant. Possibly a chain, a turn, a pause, a descent, a search, a warning, a gas-sharing attempt, and then the point where the remaining gas no longer matched the distance to safety. That is why the digital evidence matters. The physics gives us the limits. The recordings may eventually show how the group crossed them. So does the math prove exactly what happened? No. We still do not know the complete dive plan. We do not know every cylinder's exact contents. We do not know the complete cave route. We do not know what the GoPro footage shows. And we do not know the full testimony of the sixth diver. But the math does change the way we look at the accident. It tells us that 60 meters is not simply a deeper version of a normal recreational dive. It is a different environment. Gas disappears much faster. Narcosis can degrade judgment. Oxygen exposure becomes more serious. A silt-out can erase the route. And single-cylinder reserves can become dangerously small during stress or gas sharing. The tragedy may not have resulted from one unbelievable mistake. It may have resulted from several ordinary problems entering an environment where there was almost no space left to correct them. That is the question I want to leave with the Commander Puzzles community. Which number matters most? The 7 atmospheres of pressure, the oxygen partial pressure, the panic breathing rate, the distance to the exit, or the amount of reserve they may or may not have had when the first problem began. Put your calculation in the comments, but keep one distinction clear. Technical analysis can explain what was physically possible. Only the complete investigation can establish what actually happened. Until then, the most honest conclusion may also be the most disturbing. The divers may not have run out of courage. They may have run out of margin.